Alright, welcome back to ME 3121. Today we're going to start chapter 15 on chemical reactions. This is going to be our last chapter in thermal in this course. So after this lesson, we will shift it to fluids, and so we will be using the fluid book, and we'll be discussing some interesting fluid or more complicated fluid actions. So be prepared for that. Now back to this chapter 15, and this is chemical reactions. You know that we've been talking about Rankine cycles, gas cycles, but where does this energy come from? They come from burning the fuel. Cannot avoid talking about combustions if we wanted to talk about thermodynamics. But rest assured, we will emphasize less on the chemical reactions itself, like the chemistry itself. So if you have forgotten most of your chemistry, you probably will still be okay doing this chapter. We will be emphasized more on the calculations, balancing the formula, and calculating energy. So that will be the focus of this chapter. So first of all, let's define what is fuel and combustion. So combustion basically is burning the fuel. What is fuel? So anything that can be burned to release thermal energy, we consider them as fuel. Most of the fuel that we discuss in this class are the hydrocarbon fuel with CNHM, which means it consists primarily of hydrogen and carbon, and they can be combined in any sort of ratio. And the common fuels that we use a lot in daily life are coal, gasoline, and natural gas. We all know that coal is probably the oldest fuel that we have found. It has been a long time since people learned how to mine coals, and now we know that coal is a very complicated hydrocarbon. It mixes with a lot of different molecules together, so when you actually burn coal, you can actually release a lot of other gases besides CO2. So in coal, it's not just hydrocarbon. There might be sulfur, there might be nitrogen. So when you burn them, especially when it's not completely burned, then there are a lot of toxic gas is going to release in the air. So that's why the whole world right now is advocating try to burn less and less coal. China is the biggest country that burn coals, and they have recently come out with a policy that they will try to be relying on less and less, and so they are trying to reach the carbon neutral by 2060. So the whole world is putting an effort to try to burn less coal. Next one is the gasoline. You probably heard of it a lot. You probably know there's gas station, which represent gasoline, so you can add gas. So what exactly is gas? It's not the gas phase that we've been talking about. It's gasoline, which is pretty much octane, C8, H18. So you have 8 carbon. And so it's kind of a medium chain hydrocarbon. It's also usually blended with the methanol, so it can burn well. So that's gasoline. And the other one you probably heard a lot is the natural gas, and that's the one people also can dig from underground, which is primarily compressed methane. So methane is just CH4. It's a much shorter chain compared to gasoline. It burns very well. It's basically in compressed form. Usually because it's underground, and when it dig out, they got released. So you probably have heard that there's a big shortage this year on natural gas. US is one of the biggest place where people have found they just have plenty of resource for natural gas. Since we started to burn less coal, we rely on more natural gas, and this year it seems there's a shortage, and because this winter people have predicted it's going to be a cold winter. So energy is always a continuous topic in this world. So that's why we also try to find some alternative energy to help relieve this shortage of these typical fuels. So there is a table kind of show you compared to gasoline, which is the form of fuel that we're probably most familiar with in the US. Compared to that, what are some other alternative fuels that to burn compared to gasoline? So the first column shows based on the same amount of volume, how much energy they can release. And you probably can imagine usually the longer chain has a little bit more energy per volume. The second column shows when they can release the same amount of energy, how much volume they use compared to gasoline. So you see the diesel are doing similar as gasoline. And here's the only difference, or the significant difference, is methanol and compressed natural gas, and also liquefied natural gas. So those are to release the same amount of energy, they just need more volume. Okay, so now with this background, we can move on to try to calculate some numbers. Usually when we calculate combustion, we talk about the fuel is oxidized, and then a quantity of energy is released. So if we want to write out the chemical reaction equation, ideally we would say this CmHn would react with O2, and then it turn to some other molecules. But here, usually in reality, you're not going to get pure oxygen. What's more practical is you're just going to let the fuel burn with air. So if it is air, then we know that in the air there's about 21% of oxygen and 79% of nitrogen. So that means if there is 1 kilomole of oxygen present, then there will be 3.76 kilomole of nitrogen present. So sometimes we just write as 4.76 kilomole. So that's the number where it comes from. We pretty much ignored the other composition in the air, such as like argon, helium, hydrogen, and also water. And you probably already know if for the fuel to burn, the temperature has to raise above the ignite temperature. So here it shows some temperatures for the common fuels. 260 for gasoline, which is not too high. I guess that's another reason why it's used in the car. But like methane, which is the natural gas, you need 630 degree in order to actually initiate the burn. So next, to calculate the energy balancing equation, we gotta make sure you understand that during this chemical reaction, mass is going to conserve. So that has been true throughout the whole class. We're not talking about nuclear reaction, so mass is going to stay the same. On the left-hand side, mass, so for example, on this blackboard, 2 kilograms of hydrogen, 16 kilograms of oxygen, so they add together should give you 18 kilograms of water. So that should conserve. But the total number of mole is not conserved. For example, for these carbon plus oxygen, that gives you CO2. On the left-hand side, you have 1 kilomole of for example, you can say 1 kilomole of carbon and 1 kilomole of oxygen, but that does not equals to 1 kilomole of CO2. So the total number of moles is not going to conserve, but the mass is going to conserve. If you look, 1 kilomole of carbon, if you still remember your chemistry, carbon molar mass is 12. So 1 kilomole of carbon is 12 kilogram. Oxygen is 32, so this is 32 kilogram. On the right hand side is 1 kilomole of CO2 is 44. So on the right hand side is 44 kilogram. So you will notice they actually equal. Now we can define another concept. It's called air-fuel ratio. It's defined as the mass of air to the mass of fuel. So on top is air, on bottom is fuel, and the ratio is a mass ratio. And of course, you can reverse it to fuel-air ratio. So it depends on what the question asks you. And here we just want to emphasize mass equals to mole number times molar mass. So these we have seen for many times since chapter 12, 13. And for example, on the picture in the picture on the left, we have 1 kilogram of fuel and 17 kilogram of air. So the air-fuel ratio equals to 17 over 1 kilogram. So that gives you the ratio of 17. So 17 parts of air to 1 part of fuel based on the mass. So let's quickly take a look at this example to see how we're going to use the equation, and that's pretty standard for all the questions in this chapter. So you're having a octane, C8, to react with air, and after combustion you get CO2, water, excess oxygen, and nitrogen. So you know nitrogen comes from the air. It didn't really react with the fuel, so it just get left behind. So what we do first is to balance out this chemical reaction. It asks you to determine the mole numbers of each gas and find the air-fuel ratio. You're given the octane is 1 kilomole, and in the air there is 20 kilomole of oxygen. So we are going to write out the balancing equation, C8H18 plus. Now we have 20 oxygen. Remember we said for every 1 part of oxygen, you're going to have 3.76 of nitrogen. So we have 20 parts of oxygen, so overall multiply by 20. That gives you CO2, H2O, oxygen, and nitrogen. We don't know any of these, so we're going to give them X, Y, Z, and W. So those are the numbers we need to calculate. So we're going to balance based on the atoms. So let's look at carbon. Carbon on the left-hand side, we have 8 carbon. On the right-hand side, we have CO2. So that's the only carbon on the right-hand side. So that means X equals to 8. Next is hydrogen. On the left-hand side, again, only in the fuel, it's 18. On the right-hand side is the hydrogen is in water. And notice here it's H2O, so it equals to 2Y. So that means Y equals to 9. Next, oxygen. Oxygen on the left-hand side. You can do either oxygen or you can do just one single atom of oxygen. So you can either do O2 or O, so that will slightly change the equation. So I'll show you how to do just single atom. So on the left hand side, you have 20 multiplied by 2. On the right hand side, we have oxygen in CO2, so that gives you 2x. Water give you 1y. Oxygen stand alone, 2z, and that's it. And because we already calculate x and y, we can actually calculate z equals to 7.5. Lastly, we can do nitrogen standalone. Because nitrogen didn't really react with anything, you can just use it as an N2 format. So on the left-hand side, you have 20 multiplied by 3.76. On the right-hand side is just W. So that means W equal to 75.2. So you basically balanced out the equation. I would recommend you to write it one more time just so that you're clear, but you can also leave it like that if you know which one is which one. So I'm going to write it one more time. C8H18 plus 20. This is air, and become 8 CO2, 9 water, 7.5 of oxygen, and 75.2 nitrogen. So this is pretty much the mole number because this is for 1 kilomole of the octane. So the result is basically, for example, CO2 is just 8 kilomole. Now next, define the air-fuel ratio. It defined as air mass over fuel mass. Air mass, so what we said before is using the mole number to multiply the molar mass. You can actually break it into oxygen and nitrogen. But because people are doing the air molar mass so many times, they always appear together. So instead of doing them separately, we can actually just use the molar mass for air, which is 29 kilogram per kilomole. So that will be on top is air. How many mole of air? So it's 20 times 4.76 times 29. And of course, you can break it into, 20 multiplied by oxygen is 32 plus 20 multiplied by 3.76 multiplied by nitrogen, which is 28. So you will get the same number. On the bottom, the total mole number is just 1 kilomole of C8, so 8 multiplied by 12 plus 18 of hydrogen multiplied by 1. So this gives you 24.2 kilogram of air per kilogram of fuel. So this would be your final answer. All right, now you know how to balance a chemical reaction. Now we're going to make it a little bit more complicated. Because combustion sometimes is incomplete. As we said earlier, that like carbon, when it burned, it can become CO, carbon monoxide, instead of carbon dioxide. Same thing with nitrogen. When it burns, it doesn't necessarily get into NO2. Same thing with sulfur. Sulfur doesn't necessarily go into SO2 either. So for the fuel that's going to their final form, so for example, the fuel we have in our discussion is pretty much just carbon. And carbon, if it burned complete, will turn into CO2. hydrogen, when it burns completely, it become H2O, will become water. And if there's any sulfur, it will burn into SO2. So that's when the combustion is complete. So if there is remaining fuel that can be completely further oxidized to these three form or three products, then we call it incomplete. So that include, you can have carbon standalone, hydrogen standalone, carbon monoxide, or the hydroxy group. So there are many reasons for incomplete combustion. The obvious one would be you don't have enough oxygen. But sometimes even if you do have enough oxygen, even if you do have excess oxygen, there still can be incomplete combustion. It's just because the mixing is not necessarily very well. For example, you can imagine if you have a box and the fuels are here and the oxygens are here, and they just, for somehow, they never really mix with each other, then these fuels are not going to be burned completely. Another reason would be dissociation. For example, we know hydrogen plus oxygen can turn into water, but at high temperature, water will dissociate and it will separate into hydrogen and oxygen. So it really depends on the, from chemistry, you probably learned it depends on the concentration, it depends on the temperature, it depends on if there are any catalysts, then you can determine whether the reaction is going to the right or is going to the left. So this can get complicated. We don't really discuss details about that, but you need to know that because of these condition exists, and so even if you have excess oxygen, it does not guarantee you will have complete combustion. So this is just an illustration of a complete combustion process. And now we want to introduce you this concept called stoichiometric or theoretical air. Stoichiometric or theoretical combustion. So these two are combined together. So let's talk about what is a theoretical combustion. So I like to just call it theoretical. I don't use that stoichiometric because it's really long and hard to pronounce. But you need to understand if the problem states like that, you need to know what it means. Theoretical combustion is just say it is the ideal situation where the fuel is burned completely and there's no excess air. So we call it theoretical air. So the theoretical air is the minimum amount of air that need for the complete combustion. So it only works on paper. Mathematically, left-hand side atoms equals to the right-hand side atoms, and all the fuel burned completely and there's no excess air or there's no excess oxygen. So that's a theoretical. It's chemically correct, or you can say it's 100% theoretical air. Now we have talked about there's excess air. It's just there are oxygens that were not used during these combustion, so we have some excess. So it's more than the theoretical amount. On the other hand, you can have a deficiency of air, so the amount is less than the ideal number of air. And another thing we call it equivalent ratio, which is probably less used, is the actual fuel-air ratio to the theoretical fuel-air ratio. So when we say, for example, we have 50% excess air, so that means the air in the mixture is 150% of the theoretical. On the other hand, you say 90% theoretical air, you can say that's 10% deficient. So those are the terms you will constantly see in the problem. So again, this is just an illustration of the theoretical combustion. In this case, there's no unburned fuel. All the fuel reacted into their final oxidized form, and there's no extra oxygen in the product. Now, because the theoretical process is hardly ever happen, so what happened in reality is really hard to predict. Like we discussed earlier, combustion really depends on so many factors: how well you mix, how much, what is the temperature, and what is the air-fuel ratio. So there are just so many factors that can affect how the combustion goes and what are the products. So one way to actually find out what are in the product is using these Orsat gas analyzer. So this thing we briefly mentioned when we talked about gas is sharing the volume. This uses an assumption for the ideal gas. You will see here the mole fraction equals to the volume fraction. So what happened is you have this device that can absorb a certain amount of gas. So your gas sample will run through this device. For example, this device will absorb CO2, just as an example. So at the beginning, you start with a volume 1, and through this, all the CO2 get absorbed in the device, and when it leaves, this will be a sample without CO2, so you get a second volume, V2. And you can measure the volume difference between the beginning and the end. Then you can actually measure how much CO2 take place in the sample. But of course, again, this is, this equation is built upon the assumption that this is ideal gas. So you already know if the pressure is not really high, this assumption is more or less correct. Okay, so now let's do some practice about this theoretical air and excess air. So you're given the fuel, which is a composition of coal. So it has these many components, and notice here is by mass, the percentage is by mass. And it's burned with a theoretical amount of air. Disregarding the ash, assuming this part is not going to react. Find out the mole fraction of the product and apparent molar mass of the product, and the air-fuel ratio. So because it's given you in the mass ratio, and when we balance the chemical reaction, we got to use the mole ratio. So first of all, you need to change these fractions into mole fraction or mole numbers. So you can assume, say, the total mass is 100 kilogram. So that carbon will become 84 kilogram, hydrogen will become 1.89 kilograms, so on and so forth. So with that, we can calculate the mole numbers for each one using the mass of each one divided by its molar mass. So to save some time, I calculate them here. Now let's copy it into the notebook. So we found carbon is 7.03, oxygen 0.945, hydrogen. Oxygen is 0.1375, nitrogen 0.0225, sulfur 0.0278. All of these are the fuel composition. Now we need to add air, so we're asked to calculate the theoretical, so we're going to call it a theoretical. O2 plus 3.76 of N2. Now that is going to, we also know theoretical means this is a complete combustion. So that means all the C carbon turn into CO2, hydrogen turn into H2O, nitrogen is not going to react, sulfur is going to turn to SO2, and like I said, nitrogen, we consider it's not going to react. Now we are asked to find out the final mole fraction, so we don't know any of them. We just call it X, Y, Z, and W. Now you can do this atom balancing again. You're welcome to pause this video and calculate X, Y, Z, and W by yourself. Start from carbon, left-hand side. We only have carbon, 703. Right-hand side only have CO2, so X equals to X. Next one, hydrogen. We can do hydrogen as H2, then it becomes 0.945 on the left-hand side, equals to right-hand side, we actually only have CO2, or we only have H2O, so it's actually just Y. So notice here I'm doing hydrogen as H2 instead of the single atom. Next we can do O2. Again, you can do O2, so that on the left hand side there's 0.1375. We also have O2 in the air, so plus a theoretical equals to right hand side, it's in the CO2, which is X amount, H2O, we only have half of Y, because H2O, there's only one oxygen atom, and SO2, so that's Z. Next is sulfur, 0.0278 on the left hand side, right hand side, SO2 is just Z. Last one is nitrogen. We have 0.0225 plus 3.76 times a theoretical in the air equals to the W. So that means we already know X, Y, Z. From X, Y, Z, we can actually calculate a theoretical here. 7.393. And once we know a theoretical, we can plug into nitrogen. We found out W equals to 27.82. So once we solve all the X, Y, Z, W, we can find out the mole fraction for the product. For a product, we have, just write it one more time, 7.03 of CO2 plus 0.945 H2O, 0.0278 of SO2 plus 27.82 of nitrogen. To find mole fraction is pretty straightforward. For example, if you it's pretty straightforward. You just add the total mole together, so that equals to 7.03 plus 0.945 plus 0.0278 plus 27.82 equals to 35.82. Let's call it kilomole for now, since you assume the total total mass is 100 kilogram and all the numbers actually turn into kilomole. To find the fraction is pretty straightforward. For example, CO2 fraction, 7.03 divided by 35.82, that gives you 0.1963. So you can repeat that for all the other three products. YH2O is 0.02638. why SO2 is 0.000776 and N2 is 0.7767. To find apparent molar mass, you probably recall how we did it in chapter 13, and now you probably know that chapter 13 is pretty much a foundation for this chapter. So apparent molar mass equals to the total mass of the mixture divided by the total mole of the mixture in the product. So total mass would be each single mole number times each single molecule. So let's do one by one. First one, oxygen. Oxygen is 44. Next one, 0.945 of H2O, 18. 0.0278 times SO2. S is 32. O2 is also 32, so they together is 64. Nitrogen, 27.82 times 28. Divided by total mole number, we already calculated, 35.82. That gives you 30.9 kilogram per kilomole. Last one, to find air-fuel ratio, which is defined as mass of air divided by mass of fuel. Mass of air, you go back, we calculate a theoretical. And then we just multiply by its molar mass of the air. So that would give us, so a theoretical is 7.397. 7.397 times 4.76 times 29. So that's the mass of air. Fuel, you don't need to do all the mole number times molar mass again, because we assumed the fuel is 100 kilogram. And actually, you can't really do that way, because that if you do use molar mass times mole number in the equation listed here, then you will omit ash. Remember, ash, there was a 7.83% of ash that is not reacted. So if you don't use the total mass of 100, then you actually omit that. So then the ratio would not be correct. So you need to divide it by 100. That gives you 10.2 kilogram of air per kilogram of fuel. So this is the final answer. So that's it about this example. Next, let's look at something a little bit more complicated or more interesting. So this is natural gas, and using the volumetric analysis, you found 72% of methane, 9% of hydrogen, 14% nitrogen, 2% oxygen, 3% CO2. So this is the fuel composition. And notice here it is by volume analysis, so all the percentage are actually volume percentage. So that's actually very good, because we know we're going to assume all of these combustion problems, the gases follow the ideal gas law. So if it's a volumetric analysis, the volumetric ratio, for example, V of any composition over the V total equals to the mole number of the total number, right? So that's actually pretty nice. Well, you gotta be clear, this total number is total number of the fuel, right? And now it's going to burn with stoichiometric So which means it's a theoretical and then it's going to be complete. Now there's one thing that's interesting is this air has an 80% relative humidity. So that means this air is not dry air, there's some water vapor in it. But of course, we assume the water vapor is not going to add into the chemical reaction. We're just going to look at how it's going to affect the product. Determine the dew point temperature of the product. So that's interesting. How we're going to find out the dew point temperature? Remember, the dew point temperature is defined as the saturated temperature at that pressure, the vapor pressure at that state, right? So dew temperature means at that temperature, water will start to condensate, but is based on that amount of water. So pretty much we are asked to find out how much water composition is in the final product. And we know there's hydrogen in the fuel, and it's going to react with oxygen and turn into more water. So we're going to add that into account. So there will be water coming from the air and water coming from the reaction make into the final water. So that means we need to find out the balance, find out how much water generated, and then look into how much water the pressure or the vapor pressure in the final product. So let's take a look. So earlier I already said this is volume percentage. That means it's mole percentage. That means we can pretty much write it into the balancing equation. So 0.72 methane plus 0.09 hydrogen plus 0.14 nitrogen plus 0.02 oxygen plus 0.03 CO2 plus a theoretical of oxygen and nitrogen. Well, here I was using basically the total amount of mole is 1 kilomole of fuel. That's pretty much. You can assume the total amount is 100 kilomoles, so you get rid of the decimal places. So it's really up to you. You're going to get the same result regardless. And it is a theoretical combustion. Notice that if in the future it just says it's still a chemometric reaction, it might not tell you these are the final product. So you should know what are the final products. So C will turn into CO2, H will turn into H2O, and because this is theoretical, I do not have excess air, and nitrogen will stay. So X, Y, and Z. Let's quickly balance it. Carbon 0.72 and 0.03 on the left equals to right. So that means X equals to 0.75. Hydrogen, the first one is H4, so 4 times 0.72. plus 0.09 times 2, no more hydrogen, equals to 2y. So that means y equals to 1.53. Next, we can do nitrogen. Doesn't really matter the sequence. So 0.14 plus 3.76 times a theoretical equals to the final. And then we need a theoretical, which is through the oxygen. So oxygen, we have a 0.02 and CO2 0.03, and a theoretical. And in the product, I have X as O2, H2O as half of Y. Nitrogen doesn't have O2, so that's it. We can solve. X and Y are known. We can from here solve A theoretical equals to 1.465, and then we can plug it into the previous equation to calculate Z equals to 5.648. So you probably notice nitrogen probably will always be the last one to get solved because it's not really reacted with anything. So this one is the one we're interested in. We're going to use how much water it generates. But remember, there originally some water here, so we need to find out how much water originally it have and add with how much water it generate to find out how much water percentage in the final product. So how do we know how much water originally there is in the original air? We're given the relative humidity. We're also given the temperature of the air. To find out the vapor in the original air, so we can use the ratio between the pressure. So if we know the original vapor pressure over the original pressure when it came in, which is 1 atm, then from here we can actually calculate the original mole number of the vapor, and then add with Y, and we can move on to find out the moist in the final product air. Pressure at the original ATM, we know what number that is. So what is PV then? From chapter 14, we actually know that relative humidity is defined as PV over Psat at that temperature. So the temperature coming in is 20 degrees Celsius. So this equals to, we're given this equals to 80%. So we just need to find Psat at 20 degrees. So we're going to read table A4. 20 degrees Celsius, Psat is 2.3392. So that means PV over 2.3392 equals to 80%. So we can actually calculate PV equals to 1.8714 kilopascal. Now we know that PV, and then we can over the total mole of air. Notice here, this is not just the dry air here. It should be dry air add the mole number of vapor. Okay, so the total number of dry air is what we have here in this equation. So that's the amount of dry air. But remember, originally there is the vapor mole number there as well. So we're going to write as N over N plus N air. So we can write one more step, plugging in. NV is the one we're going to calculate. The total amount of air, we calculate A theoretical is 1.465 and multiply by 4.76, that gives us 6.97 kilomole. So 6.97 equals to PV 1.8714 divided by the atmospheric pressure 101.325. So kilopascal. Now you can solve for NV, which equals to 0.131 kilomole. So once you solve for NV, you can check moist in the product air. which is 0.131 kilomole plus Y. So Y we found out is 1.53. That gives you 1.66. Remember, we're going to find out the dew point temperature. The dew point temperature is the Tsat at PV in the final. So that means we are going to find out PV in the product. And we can use the same equation, PV of the product over P total, which again is stay as 1 atmosphere pressure, equals to NV of the product divided by the total total mole of the product. So that is NV, we already found, 1.661. Total, we have X, Y, and Z plus our little vapor, which was not counted in the reaction equation. So you can write as X plus Y plus Z plus 0.13. So that equals to 1.661 over 8.059. 1 ATM is 101.325 kilopascal. And make it to the other side, we come to PV in the final product is 20.88 kilopascal. So dew point temperature is Tsat at 20.88 kilopascal. Then we can go back to check the table. We can check A5 or A4, so let's see if we can have 20.88. So it's close to 20, so that means the Tsat is going to be around 60. So you can do an interpolation, or you can kind of estimate it should be close to 61, right? Because 20 is 60, 25 is about 65, so 21 kilopascal is about 21 temperature Celsius. So you can do a proper interpolation, then that gives you 60.9 degree. So that's the final answer of this question. Okay, let's look at one last example. So this is a reverse combustion analysis. This one gives you the product and asks you how much air was using. So you notice the product still has unburned fuel, so you know this combustion is not complete. But you also notice that there are excess air or excess oxygen in the product. So whether you have excess of air or deficient of air is actually unknown. So you have to do the calculation to conclude. But from excess fuel, you can conclude this is an incomplete combustion. But you cannot say that there is deficient of air. So that's going to leave to the calculation. It also asks you to calculate how much percentage of theoretical air used. So that means you need to calculate the theoretical air and then compare this reaction to the theoretical reaction. And then it also asks you to calculate how much H2O water condensed when the product cooled to 25. So it's very similar to the previous problem. So it's going to test your knowledge on chapter 14 again. So that will be your chance to practice that again. So let's take a look at it one at a time. So this fuel is just octane. We can write out octane plus A. Now this time it's not theoretical, so O2 plus 3.76 N2 equals 2. You're given these ratio, and the ratio is based on volume. So you already know based on volume means those are the mole fraction. So you can assume, say let's do assume this time product gas N equals to 100 kilomole. So now we just get rid of the percentage this time. It's up to you. You can still use 1. It's not really crucial. So 10.02 of CO2 plus 5.62 O2 plus 0.88 CO plus 83.48 N2. And one thing I didn't mention is H2O, because you have H in the octane, so there will be, let's call it B amount of H2O. Now besides that, we don't know how much octane we have either, so that's why this is a reverse analysis, so let's call it X. So you can do the same thing, doing a chemical balance, carbon, 8 of X equals to final 10.02 in CO2 plus 0.88 in CO. So that gives you X equals to 1.36. Next, hydrogen in the reactant, 18 times X equals 2. So the only thing has hydrogen is water, so that's 2B. Because we already calculate X, and so we can calculate B actually is 12.24. And N2 is 3.76 times A equals 2. In the end, you only have one N2, 83.46. So you already calculate A equals to 22.2. So you notice you actually only have 3 unknown, and till now you already calculate 3 unknown. You can write out the O2 function, then you will notice they should equal. Hopefully they equal, otherwise your calculation is wrong somewhere because you have one excess equation, so this equation should be redundant. So let's take a look. O2 on the left hand side is just A. On the right hand side, CO2 has 10.02, O2 5.62 plus CO 0.88 divided by 2, H2O B divided by 2. So you can find out A on the left hand side is 22.2 on the right hand side. So this is 0.44, this is 6.12. So you can add them up. You should get also 22.2. Okay, so hopefully this equals, and you check all the 3 A, B, and X numbers are correct. So this is like you have an extra given condition. So that being said, next time in the future, that we don't have to give you all the numbers of these products. So we can hide one. You should still be able to calculate. Yeah, so for example, I can also hide the nitrogen. You should still be able to calculate the balancing equation. So, okay, so we found out all the balancing mole numbers. We're asked to find out the air-fuel ratio. Don't forget what we're asked for. So air-fuel ratio is mass of air times mass of fuel. Since we already found the mole numbers, we can just calculate directly. So 22.2 times air, 4.76 times air molar mass, 29, divided by fuel is 1.36 x times C8 is 8 times 12. 18H is 18 times 1. That's 1 molar mass for octane. That gives you 19.76 kilogram of air over kilogram of fuel. Pretty straightforward. So this is the first part. Second part, it asks you to calculate how much percentage compared to theoretical air. So that means we need to calculate the theoretical reaction. So still octane react with air. So now this time a theoretical O2 plus 3.76 of N2. Now it's going to give me, now this is theoretical, so it's going to be complete reaction. So we have CO2 plus H2O plus N2. Okay, so we don't know any of them. We call it X, Y, and Z, and balance out this equation quickly. Carbon, left-hand side 8, right-hand side is X. Hydrogen, left-hand side 18, right-hand side 2Y. So Y equals to 9. Oxygen, left-hand side, a theoretical equals 2, right-hand side X plus half Y. We already found X and Y. So a theoretical equals to 12.5. Last one, nitrogen, 3.76 times a theoretical equals to Z. So Z equals to 47. So that's it. Now we're asked how much the actual air compared to the a theoretical. So we should just use air of actual over air of theoretical. Since the molar mass is the same for the actual and theoretical, we're talking about air. So basically it boiled down to the mole number of air in the actual over mole number of the theoretical. So that should be, so earlier we calculate A equals to 22.2, but pay attention, this 22.2 is corresponding to 1.36 of fuel. But here, the A theoretical we calculate, 12.1, is corresponding to 1 kilomole. So when we compare how much theoretical or how much excess air or deficient of air, we got to compare to when it's burned to same amount of fuel. So that means what I can do is I can divide these 22.2 by 1.36. So then that will give me how many mole numbers to burn 1 kilomole of the octane. Divided by 12.5, that gives me 1.305. So that means we are using 130.5% of theoretical air, or you can say 30.5% excess air. Okay, last part. So the question asks you how much H2O is going to condense when the air is cooled to 25. And notice here, originally we have just dry air, so originally there's no water. So it's a little different from the last one. It's actually make things a little easier. You don't need to worry about how much original water is there. then it's going to make things a little bit more complicated. Now to find out how much it condensed, we just have to assume that it actually condensed at 25. So that means the dew point temperature is actually higher than 25. So by 25, it already reached to its dew point and already water started to condensate. And we're asked to find out how much condensate. What we can do is find out how much first, what we can do is to find out how much total water in the product that generated. Then we can find out at 25 degree what is the saturated. So, right, so total amount of water in the product less than how much saturated. The saturated one will still stay in the air, right, or in the gas mixture. So then the difference is how much mole it actually condensed. So now the next question would be, how are we going to find out what is the saturated mole number or the saturated fraction in the final product? Well, then that's going to go back to the saturated pressure ratio equals to the saturated, or equal to the mole number. So let's write things out. We assume, first of all, the dew temperature is greater than 25 degree, so that there will be water condense. Then we assume moist condensed is NW mole number. And we can also calculate the total number of the final product. We haven't done that, so we need to add everything together, 10.02 and everything else plus B, right? So we'll just do that. 10.02 plus 5.62 plus 0.88 plus 83.48 plus 12.24. That gives me 11 or 112.24 kilomole. Now, after water condensed, the air is saturated. So the final air is saturated. We can still write out the mole ratio or the fraction equals to the pressure ratio. So the mole number left of the water mole number left in the air would be 12.24, that's how much it generated, less than how much it condensed. And the air mole number becomes 112.24 minus the condensed, because once it condensed, it's no longer in the air. So that should equals to P vapor over the P total in the final. And P vapor, this is saturated, so it's P sat at 25 degree. We're told the final temperature is 25 and final pressure is 100. So that over 100 kilopascal. We just need to check the water table at 25 degree. 25 degree, the saturated pressure 3.1698. Put it back. 1698. All right, so looks like we only have one unknown and one equation. We should be able to solve for NW, which is 8.96 kilomole. So 8.96 kilomole condensed in the end. If you compare my work with the book probably divided by So the book probably calculate the condensed water based on 1 kilomole of fuel, but this number is based on 1.36 kilomole of fuel. So that's the difference. But still, you can calculate how much percentage it condensed. So that will be 8.96 divided by 12.24, that's how much it generates, equals to 73%. So 73% of the generated water actually condensed and left as water liquid. So that's the final answer for this question. Make sure you really understand there's a combination of what we learned in chapter 13 and chapter 14. So chapter 15 in itself is not that difficult. Really, you need to understand the several concepts and balancing the chemical equation, which also doesn't require so much of your chemistry knowledge. All right, before you go, there's just one last concept that I would like you to know. It's called the heating value. So when we mention about heating value, it just means how much energy is going to, how much heat is going to release when the fuel is burned completely. Sometimes we use these terms to talk about, for example, in the boiler, the coal has a heating value. So this number is usually considered as given. So when it's give you, so for example, we say the coal heating value is whatever X amount of number. And then if you're going to burn 100 kilogram of coal, how much energy you're going to release. So that would be heat releasing would be 100 multiplied by X. So you just need to know that in case any problem using this term heating value. So that's it, and that's all you need to know about chapter 15. And like I said, after this chapter, we're going to stop talking about the thermal book and we're going to transit into the fluid topics. So see you next time.